Hi, my name is Paris Skiris, and this is Lab 2, Lines of Charge. The purpose of this lab was to take our findings from Lab 1 and then apply them to a line of charges instead of a point charge. In the first lab, we treated the two tapes as point charges, where now we treat them as line charges. And then we used Python to create a computational model to show the charge of the tape. In Lab 1, we took two positively charged pieces of tape and placed them near each other in order to find out what the charge of the tapes was. It was found that both pieces of tape were positively charged. In my case, when tape A was held to tape B was displaced by 0.015 meters in the positive y direction. This is one of the reasons I was led to believe that they had the same charge. This is a quick overview of the calculations that were performed in Lab 1. By using the different formulas and laws that we learned in class, we were able to find the following: the mass of the tape, the gravitational force on tape B, and the charge on tape B. We were also able to find the number of excess electrons in the tape, the number of atoms on the tape, and the ratio of atoms to electrons in the tape. The bulk of Lab 2 consisted of coding in Python to create a computational model. In the first part of the code, we defined the variables that were to be used, we made an estimate of the charge on one of the pieces of tape, and defined a function that produced the value of the electric field for a charged particle. In the next part of the code, we used a function that created a line of uniform point charges for an n number of point charges that we had defined earlier. This is the function that allows us to show the tapes as lines of charge instead of just point charges. This is important because in reality, the two pieces of tape are in fact lines of evenly distributed charge. Modeling the tapes as lines of charge will help us better see how the tapes are charged. The red arrow shows the for loop that creates an n number of point charges that will be shown in our model. This part of the code is where we calculate the electric field and the electric force for the tapes. The top arrow shows that the lines of codes that create the visual objects that will display the top tape and the bottom tape as a collection of evenly spaced point charges, therefore creating a line of charges. The bottom arrow shows the function that allows the electric force that the bottom tape exerts on the top tape to be calculated. This is the last part of our program. This function creates two resultant vectors as arrows and aligns the bottom of these arrows at the top tape. It also creates the visual objects, arrows in this case, that will show the magnitude and direction of the electric force vector and the gravitational force vector. Finally, the code will print the calculated values of the magnitude of the electric force on the top tape and the magnitude of the gravitational force on the top tape. We will also see an interesting finding in the computational model that was created by our code. We have finally gotten our computational model for our code. Now we can see the tapes as lines of charge. The red objects represent the line of charges that depict the top tape. The blue objects represent the line of charges that depict the bottom tape. The green arrows show the electric field of the top tape. The white arrows show the electric force vector, that is the net electric force on the top tape. And the yellow arrow is the vector that shows the gravitational force vector on the top tape. Our interesting finding that I mentioned earlier is that the magnitude of the electric force is equal to the magnitude of the gravitational force. This can be proven by Newton's second law that states the sum of the forces, in this case the y direction, is equal to 0. This is just a short comparison between the Lab 1 and Lab 2 computational models. We can see that the Lab 2 model shows us a more realistic representation of the forces acting on the tapes. These are some questions that can be answered with our findings from this lab. The magnitude of the charge on one piece of tape calculated by the computational model is 9.01442 times 10 to the negative 9th coulombs. The assumptions that we can make are that we can ignore air resistance. We can assume that each U-tape made had about the same amount of charge evenly distributed along the length of the tape, and that we cannot treat a long tape as though it were a point charge with all the charge concentrated at the center of the long tape. The charge if the tapes were modeled as a single point charge would be 6.969 times 10 to the negative 9th coulombs. These estimates differ because the point charge only gives us the charge at a single point on the tape, and the line of charge model is more likely to be closer to the real value because it provides an average charge over the length of the tape.